Okay. Well, what is electronegativity? It's just a measure of how much an atom in a bond wants electrons. So we've done this before. If this is element X and this is element Y. If Y has a high electronegativity, say it's 3.0, and X has an electronegativity of say 1.8, then the electrons are not going to be shared equally here. They'd be drawn much more over to the Y atom, which would make this somewhat negative and this somewhat positive. So electronegativity is how much the atom wants the electrons in the bond. And in this case, Y wants it much more than X. Of all the elements on the periodic table, fluorine is the most. So again, the trend is these are going to be very low, oftentimes under 1 or low 1s here, moves over usually under 2 here, and then over here is where the electronegativity gets larger, but fluorine is the one that is the most electronegative. So if we have molecule AB and A is more electronegative than B, that just means unequal sharing, and it's got to be obviously closer to A. Alright, now we get into intramolecular forces. So we've talked about intermolecular forces. Those are between. So again, this is an intramolecular bond here. But an intermolecular bond is one where we've got an attraction. It's not an actual bond, but an attraction between one molecule and another molecule. So I just did light dashes here. This chlorine is going to be attracted to this hydrogen because there's a dipole. So hydrogen is somewhat positive, and chlorine is going to be more negative. And so there's going to be an attraction here. The stronger that attraction is, the higher that the melting points tend to be. Well, in the situation where we have hydrogen and chlorine like this, a dipole in this molecule and a dipole in this, we call this a dipole-dipole intermolecular bond. There's a special subcategory of dipole-dipole ones. So these are our dipole-dipole attractions here between oxygen and hydrogen. But because oxygen, again, is in this second period, we're going to say if it's between nitrogen and hydrogen, oxygen and hydrogen, or fluorine and hydrogen, that qualifies for a special subcategory of dipole-dipole intermolecular bond that we call a hydrogen bond. So since those are more strong, then that makes water have a higher melting point and a higher boiling point. So when I go like this, I just pour a little bit of water here, and I run my finger through it, what I'm doing on the molecular level is I'm running my finger here. I'm not breaking oxygen and hydrogen apart, but I am breaking water and water attractions apart. And then lastly, when we have when we have molecules that are non-polar, so I just use this as an example, we can have London dispersion forces or van der Waals forces that are much less significant than hydrogen bonds or dipole-dipole. And the way they form is, if this is situation A, can you see how when this one starts to get closer, the electrons don't want to be near each other, and so then they might move over here. And when they move over there, then we're going to have a little bit of a positive-negative attraction here. And it only exists for a split second. But it is a small attraction nonetheless. We call that a London dispersion force. Alright, well, given that, then we can illustrate dipole-dipole, hydrogen, and London dispersion forces. These are the hardest to kind of illustrate. But hydrogen is going to be the strongest, dipole-dipole is going to be the second strongest, and then much lower in terms of strength is going to be the London dispersion forces. Next question here. When intermolecular forces are high, the compound will have a higher boiling point. That's why something like water, which has that significant hydrogen bonding, boils at 100 degrees, whereas something like alcohol, which won't have as strong hydrogen bonds, would boil at a lower temperature than water would. Alright, now when we do these, you've got to draw the structure of each of these and then ask yourself, well, first off, would the molecule be polar or nonpolar? And then, as a result of that, what kind of intermolecular forces would be present? So, you know that for water, that's going to be hydrogen bonding. When you draw this one, this will come out to be nonpolar. So then the only type of intermolecular bonding there would be the London dispersion forces. In this one here, this would be a polar molecule, and there will be attractions between chlorine on one molecule and hydrogen on another molecule, similar to there are here. But that will be dipole-dipole, which won't be as strong as a hydrogen bond. And the reason there is chlorine is in the third period, and so those electrons are not as concentrated around the nucleus of chlorine as they would be were the electrons in oxygen, because oxygen's in that second period. So that would be dipole-dipole, and then here C2Br2, that's the example we saw on the previous page. So then we'd be back to nonpolar, so that'd be only London dispersion forces. Okay, as a result of that, the boiling point will be highest with H2O, and it'll be lowest with the C2H4. CH2Cl2 would be intermediate, and that would apply to all of them, whether it's the boiling point, whether it's the viscosity, how much they stick together, or whether it's the surface tension.